Hello, my name is Micaela Jurado, and today we're going to talk about Lab 4 circuits. So, the purpose of this experiment was to predict the behavior of circuits containing resistors in series and parallel. So, we're going to examine the behavior of ohmic resistors and capacitors using our circuits given in the lab. We're going to use multimeters to measure experimental values of conventional currents and potential differences. We found that our current 1 is going to equal to current 2, which is going to equal to 0.02 in the series circuit. Calculated values and experimental values for current and potential differences matched. The greater the resistance of an RC unit, the longer the time for the capacitor to charge or discharge. And RC experimental value is going to be 7.5 seconds, and RC op is going to be 6 seconds. So here are the fundamental principles we're going to use. First one is going to be node rule, which is going to be current flowing to a node must be equal to the current flowing out of it, and this is a result of charge conservation. As you can see, it's like that. And then loop rule is going to be the sum of all the electric potential differences around the loop is 0, as well as result of energy of conservation. And Ohm's law, we're going to use this specific formula for current, and it's current through a conductor between 2 points is directly proportional to the voltage across 2 points. So in part 1, charge conservation and energy conservation in series circuits, we're going to predict that current 1 and 2 would be measured by 2 ammeters. So we're going to first calculate our total resistance total, which is 47 ohms plus 100 ohms, which is going to be 147 ohms. The current will stay the same everywhere in the series circuit. And using Ohm's law, which we're going to derive I, which is current, is V over ohms, so resistance. So it's going to be 0.02 amps. And in experimental results, it's going to give us 0.2 and this is if it's backwards, it's going to be negative 0.2. So in our potential versus position graph, we have here our circuit in parallel. And here are the positions, and here are the volts. So from B to A was 2.9, C to B it was 0, D to C negative 0.9 volts, E to D it's 0 because it's flat, F to E it was negative 2 volts, and then F to G and G to H is all going to be 0. Also F to H is also going to be 0. And the potential difference, as we can see, is 0. So this follows the loop rule. And as we can see, our I will be 0.02 amps. So in part 2 is RC circuits. We're going to use 10 ohm bulb, 20 ohm bulb, a 9 volt battery, and a 200 mF capacitor. This is the overview of our 10 ohm bulb. So here it's connected from capacitor to bulb and not connected to battery, and here's connected to battery to capacitor to bulb. So from battery to capacitor, it's gonna be really bright and get dimmer, and then the capacitor is gonna be charging, and the current is gonna decrease all the way down to 0. But in the 10 ohms disconnected to the battery, it starts off bright and goes dim, same as this one, but the capacitor, instead of charging, is gonna be discharging, and the current will also decrease to 0. And for it to go completely out, it was 15 seconds. So part 2 of the RC circuits on the 20 ohms, it's the same concept, only for a higher resistance bulb. So capacitor to bulb, capacitor to bulb, no battery, and battery to capacitors over here, and to bulb. So explanation for the 20 ohm bulb is kind of the same, just that it took longer for it to completely turn off when it's connected to battery to bulb and capacitor, but if it was only connected to capacitor, it took shorter time. So this is our time dependent across discharging capacitor for 30 ohms. Here's the time and the natural logarithm of B over V initial. And this was our time, our line. And then our experimental RC was 6.42 seconds by using 1 over slope. And our calculated RC was resistance times capacitance, which was 30 times 0.2, which was 6 seconds. So very close. Human errors would have been a possible error because of miscalculation or like messing up the timing, but also being devices being faulty can also be a potential error. So discussion question 1 asks, if you were doing this lab in real life and used an actual ammeter instead of a ideal simulated ammeter, what would be different? So a real ammeter cannot have zero resistance, but in virtual it can have zero resistance. So when you connect an ammeter to resistance in real life in parallel, some of the current is going to go through the resistor, but that's not going to happen in the virtual one. And in discussion question 2, it asks like, what if you were to do this lab in real life and use a real life battery to charge the capacitor with no resistor in the unit in the circuit? So if we were in the simulated model, since there's no resistor in the circuit, we would predict that the capacitor would charge instantaneously, but in real life, and we were used to use real life batteries, it would take time to charge instantaneously. So that'd be all for this experiment. Thank you so much for watching.